Hello Warriors, this is Miss Lemons, and today I will be walking you through an introduction to waves calculations. Before we get started, make sure you have your introduction to Electron Energy and Light worksheet out in front of you. It has two formulas at the top that are in large bolded letters. We're going to label those formulas right now. So we know that there is an inverse relationship between wavelength and frequency. That means that as one variable, like wavelength, increases, the other variable, like frequency, decreases. They do the opposite. This right here is the wavelength formula. C equals lambda F. Let's label what each of these variables means. So C is the speed of light in a vacuum. The value and the units for that is 3.0 times 10 to the 8th power meters per second. Meters per second. Now this is a constant, so it's always going to be given to you. You could think of it as like the constant of Avogadro's number being 6.02 times 10 to the 23rd power, right? So this is always given to you. It never changes. The other variables we have are lambda, which is wavelength. I like to think that it looks kind of like a wave, a little capping wave, cute. And it's measured in meters. Think about the name, length, wavelength. We measure length in meters. That's lowercase m for the symbol. And then finally we have the F. F is frequency. That's how frequently a wave occurs. The units for that are hertz, capital H, lowercase z. Now before I move on, it's important for you to note that it doesn't matter if you're working with radio waves or if you're working with visible light, red light, purple or violet light, X-rays. It doesn't matter how dangerous or energetic something is. All light travels at the speed of light. All light travels at the speed of light. That means all light travels at the same speed in a vacuum. For the purposes of this class, all of our reactions, all of our calculations, they're all going to happen in a vacuum. So all light travels at the same speed. Okay. Moving on. Now, we also know that there is a direct relationship between frequency and energy in the wave. That means that as frequency increases, then the energy would also increase, and then the opposite would be true. If frequency decreases, then energy would also decrease. The formula that we use to represent that is E equals HF. Capital letter E stands for energy, and we measure energy in the unit joules, represented by a capital letter J. The H is Planck's constant. The value and units is 6.626 times 10 to the negative 34th joule seconds. So this is also a constant like the speed of light, so this will also be given to you. You don't need to memorize it. And then, of course, F is still frequency, and it's measured in hertz. So whenever we are going through each of these equations, these waves problems, I like to use the Sue's method, which is pretty similar to the Sucks method. You write down your starting value, you are writing down the unknown unit you're looking for, and instead of picking out a conversion factor, you are picking out the equation or equations that you need to use. And then finally, we set up and solve by plugging the information into our calculators and then rounding to sig figs. So the first question that we have says, what wavelength of light does 14,000 hertz correspond to? And then we have our constants given to us. Now, before I even go into this, I'm really paying attention to the words that are being used. You see, if you ever see the word wavelength, then you know that you're going to be using this formula, C equals lambda F, because wavelength is in this formula and it's not in the other formula. All right, so what wavelength of light does 14,000 hertz correspond to? Okay, so we have our starting value, which is 14,000 hertz. 14,000 hertz, what's that? That's frequency. And I'm going to write that down because I'm still trying to get familiar with the variables and the units for these. And my unknown is wavelength. So I'm going to write wavelength, and I'm going to just put it lambda, and then that's in meters, so I don't forget. Okay, so of the two equations that we have here, notice how this doesn't have any lambda in it. This is the only one with lambda, so that's why we're going to pick this equation. And then finally, we just need to set up and solve. We know that we're looking for lambda. We have been given frequency, so we can plug that in for F. And then C is a constant, so we can just take C and plug it in here. So your setup should look something like this. So we are trying to isolate lambda here. And to do that, we would just perform one-step algebra problem. To get lambda by itself, we would divide both sides by 14,000 to cancel that out on one side. Make sure that when you put this into your calculator that you put parentheses around your scientific notation so that your order of operations doesn't go wonky. After you put this into your calculator, we end up getting lambda to equal 21,428. But of course, we do need to round according to the rules of sig figs. You never pay attention to constants. You only look at what you were given at the very beginning. 14,000 has 2 sig figs in it. So we need to round our final answer to 2 sig figs. I'm going to underline my top 2 place values. In this case, I'm rounding down. So my final answer is 21,000. Remember that the unit is meters. And this would be your final answer for that first practice problem. Let's take a look at another practice problem. Number 18, calculate the energy associated with frequency 8.5 times 10 to the 8th hertz used by cell phones. So just as another aside here, if there is a problem that says anything about energy, then we know that we're going to be using the energy formula because the wavelength formula doesn't have energy in it. This is the only one that does. So let's go ahead and plug in what we know. So our starting value is 8.5 times 10 to the 8th hertz. And that is my frequency, which I also like to label with the variable, so I remember what's going where. My unknown is energy, and that is measured in joules. So I put number of joules and E equals energy. And then of the two formulas, I'm going to be using the energy formula. And then I just need to plug and chug, set up and solve. I know that frequency, F, is going to be going in here. And I am looking for the number of joules. And then finally, we have Planck's constant for H, and that can be plugged in right there. So your setup should look like this. 6.626 times 10 to the negative 34th joule seconds times 8.5 times 10 to the 8th hertz. No algebras needed here. We just need to multiply these two values together to get our final answer. Make sure that you put parentheses around each piece of scientific notation so that you don't mess up your order of operations. All right, when we plug this into our calculator, the raw unrounded answer is 5.6321 times 10 to the negative 25th power. And then, of course, we do need to round according to the rules of sig figs. We do not look at the constant. We look at the value that we're given in the word problem. That's 8.5 times 10 to the 8th. This has 2 sig figs, so our final answer should also have 2 sig figs. I'm going to underline my top 2 place values. This time I'm rounding down, so my final answer should be 5.6 times 10 to the negative 25th joules. And that is how you solve an energy equation.